Hi everybody, welcome to my YouTube channel on theoretical physics. And I'd like to begin this week with a quantum field theory review blog. And this week we're going to start doing, it might take several videos to do this. We're going to start with, so this is the sixth video, let's call this 6A because it's definitely going to be more than one video. QFT review blog. And we're going to cover Peskin, or start covering Peskin and Schroeder. Chapter 3 on the Dirac field. Now, this is a long chapter in Peskin and Schroeder, and it's got a lot of formulas and everything, and you have to really become familiar with it. For those who are using Peskin and Schroeder, it has an approach which some like and some don't. The basic approach of Peskin and Schroeder is to try and get the calculations as soon as possible. So it's sort of like kind of assumes that you've almost seen the Dirac equation before it even hits you with all these formulas in chapter 3. And as they mention, they take a different approach, which I'll get to in a second. So PNS sort of recommend that students at some point in time, either before or after studying their chapter 3, that students study, the single particle Dirac equation. It is probably one of the most important, if not the most important equation of 20th century physics. So it's very important to sort of be thoroughly familiar with this equation. Also, there are different representations, and I'll get to that in a second. So it's nice to be familiar if you look at different books and you see a different representation, not to freak out. Anyway, some preliminary books that you might, I recommend the following. These are old books, but they're still good, and there are a lot of new ones that you can read as well. Sakurai has an excellent book on advanced. This is not his quantum mechanics book. Don't confuse it. This is a different one. It's called Advanced Quantum Mechanics. Take a look at chapter 3. Schiff has a quantum mechanics book that was standard for a long time. It's old. It goes back to 68, third edition. Quantum mechanics. Look at chapter 13. And the best reference I recommend is Bourgain and Gell. Relativistic quantum mechanics. This goes back, this is their landmark 2-volume work in 1965. But volume 1, the first part just covers the Dirac equation in a very thorough way. So this is sort of what I recommend being familiar with. If you're not familiar with something like this, you're going to find this chapter very hard. Not impossible, but hard. So Peskin and Schroeder, they take a classical, sort of what they did with the Klein-Gordon equation. Rather than thinking of it as a quantum mechanical equation, they just think of it as a classical field equation. They take a classical field theoretical approach to the kg and Dirac equations. And then they quantize them using the canonical quantization procedure. Later in the book, Peskin and Schroeder developed the path integral approach for photons, and but right now they're just doing canonical quantization procedure, and it worked in chapter 2 for the Klein-Gordon equation. For the Dirac equation, we'll find out that the Dirac equation will only work, this will only work if we modify the procedure by using anti-commutators for the fields instead of commutators. So instead of, like, this would be like, say, psi I, psi j, and then the canonical thing, psi I daggers, psi j, and psi I dagger, psi j dagger, these two are equal 0, and this is going to be equal to some kind of like I h bar delta function. Okay, instead of the commutators, psi I. So that's the difference between bosons and fermions. And the Dirac equation, as we'll see, will apply to spin 1/2 particles. So they're fermions, and they require anti-commutators. And this is one of the great successes of the of quantum field theory, is understanding why commutators are used for bosons and anti-commutators are used for fermions. And this is definitely a part of quantum field theory, as we'll see in my Czernicki videos on quantum field theory. You'll see that for a non-relativistic quantum field theory, you can have either commutators or anti-commutators for bosons or fermions. They both work for spin 0. So that's a difference. But we'll get to the PCT theorem and spin statistics and all that. Title of a book. So let's just talk about Lorentz invariance, covariance. I'm using the same terminology. I'm not going to differentiate between invariant and covariant. You know what they mean, and the fact that scalars are invariant and don't change, and vectors are like covariant and change, but the equations and so on, Lagrangians and so on. So we'll just, I'll just always use the term, one of the others, and not worry about it. So because we use the Lagrangian formulation, which is essentially the least action principle, because we're using this principle, it's very easy to get easy to derive covariant wave/field equations, especially at the classical level. And the answer is just make sure, just make the Lagrangian a Lorentz scalar. And the reason for this is if you have, like in one reference frame and you have an extremum, the reason is that extrema will map to extrema if they are scalars. So that sort of gives us a way to do what we want to do, and start with the general transformation. Of an n component object under a Lorentz transformation lambda. So lambda in these notes and in Peskin Schroeder, it's always a Lorentz transformation. And for right now, I'm only dealing with proper, I forgot the exact terminology. We're only dealing with the restricted Lorentz transformations. We're not dealing with parity or with time reversal or with parity times time reversal. So the determinant, it's proper, the determinant is 1, and it's what they call, well, the term slips me right now, isochronous or whatever. The time component is maintained, it's not reversed. So we're dealing with an element of the restricted Lorentz group. I think the determinant equal 1 and lambda 0, 0 is greater than or equal to 1. Everything that I say about Lorentz transformations and generators and everything, things that Peskin and Schroeder just pull out of thin air, all of this is covered in detail in Weinberg's volume 1 of his QFT trilogy, chapter 2, and in Coleman's QFT lectures, chapter 18, I believe. So if you want more detail, those are the first couple of places I would start. So the law of transformation is going to be phi ax will go to MAB, depends on the Lorentz transformation lambda. This is the matrix associated with lambda. Phi B lambda inverse x. So just as an idea for scalars, M is just the identity matrix. We don't mix up components for scalars. There's just one component. And, for vectors, we would have a vector representation, which the book gives. I won't put it down. But there are others. There are tensors, several component objects, and most importantly, there are spinors. So this was the big discovery that Dirac made. He discovered the spinor representation. I believe mathematicians in the early 20th century were aware of these things, but physicists weren't. And then physicists sort of rediscovered them. Cartan, I believe, was maybe the first one who discovered spinors, mathematician. So to understand this is obvious. Whenever you transform objects like vectors or tensors, you have some big matrix and you're going to transform indices and everything. This is the thing that you want to understand, the lambda inverse x. And to understand that, let's just draw a diagram. First of all, I'm going to deal with active transformations. In quantum mechanics, quantum field theory, most books, most of the time, use the active approach as opposed to the passive approach, sometimes used in special and general relativity. And the difference is that we're going to keep the coordinate systems the same. Coordinate systems remain unchanged. And objects move. In this case, objects are fields. So, for instance, if we have a scalar field, let's say we have a field which has support only in like an area like this, under, let's say, a rotation, it might move to here. So if we want to know the value of phi at this point, say we want to know phi at x prime, that's where it moved to. It was originally at x, and we have x prime is equal to r, a rotation, times x. So the value here is the same as the value there. So what we have is phi at x prime is equal to phi at x, which, and this equation implies x equal to r inverse x prime. This is equal to phi at r inverse x prime. Now there's something else. I should probably put in that phi prime at x prime equals, because the field, if we had vectors and everything, the components would change, but for a scalar it doesn't change. So this is what happens with a scalar. I don't know what happened there. That's the picture for a scalar, and the picture for a vector is similar but a little bit different. Here we imagine we have some kind of area. This is where the support is, and we have like a vector. It's a vector object. It's pointing in a certain direction, and we rotate it, to here. And you can see when you rotate this thing, not only does where it's located rotate, but the actual vector rotates as well. So here you can see that we're going to get something like we're going to get, let me just show it. Let me use a different notation for a vector. We're going to get like V prime of like I at x prime is equal to, now we have the rotation matrix like Rij Vj, and so we want to go back to where it was, and then we want to apply it at that point, R inverse x. So here we get the MAB part when we rotate vector components. This will rotate, this sort of brings it back to the point from the rotation, and this thing actually rotates that vector. Okay. So now P and S rather quickly develop the Lorentz algebra. This is sort of like Lie group theory and everything, but they don't really want to go through all of that, so they develop the Lorentz algebra. They do it by analogy with the three-dimensional rotation group. But they don't actually like do it. They just sort of put down the answer. So that's why I recommend you go to Weinberg's book or Coleman's book or various other QFT books which give more details. So what we're looking for is irreducible representations of the Lorentz group. And they just sort of write down, just by analogy with the three-dimensional case. And most books use the M instead of J here, but these are like the infinitesimal generators of the Lie algebra. And it's a long formula. It's all, every term is the same. You just got to like switch indices on each term and get the right signs. Eta is the Minkowski matrix. And in Peskin and Schroeder, that is 1 minus 1 minus 1 minus 1. Okay, minus eta u rho j nu sigma minus n nu sigma j mu rho plus n mu sigma j nu rho. Okay. So what's going on here with the J's, they're anisometric. So in 4 dimensions, there are 6 of them, and they correspond to 3 rotations and 3 boosts, which works out for special relativity. So we can see we're on the right track. So these are the generators of the Lorentz group. Now, from here, we go to the Dirac equation. So we're looking for spin 1/2, and it will turn out we're going to need a 4-dimensional representation. Now, I'm going to warn you, this is something that confused me a long time ago, and this is important. When I was studying Borkin and Drell, I was very confused on some of the equations. And the confusion is that we have a four-dimensional spinner rotation. That means there are four components for each spinner. But this has nothing to do, I mean, it's related and it interleaves with, but you have to think of this as different from the four dimensions of space-time. So sometimes you'll have like a space-time matrix, and they'll commute it with like a spinner matrix, and you say, what's going on here? Well, they're acting on different spaces. We have spin space, which is 4D, and we have space-time, which is usually 4D. Not always. Sometimes we work in 10 dimensions, sometimes 6 dimensions, sometimes 2 dimensions, so on, modern physics. But keep that in mind. So Peskin and Schroeder just put down, first thing they do is they put down what they call the Dirac algebra. I think it's also referred to quite commonly as a Clifford algebra. And here, for some reason, they use G mu nu. That's the same thing as eta mu nu times 1, the identity matrix. I guess they're doing this in general for an n times n approach, so this would be n-dimensional. But they'll quickly go to 4. So this is the main relation of the Dirac matrices of the Clifford algebra in 4 dimensions. And from this, one can show, and I'm not going to do it, but it's a calculation, that S mu nu, which is defined equal to I over 4 times the commutator, gamma u, gamma nu. This is a representation of the Lorentz algebra. Remember the J's above. Now, it's also important to realize that there's many different sets of matrices that satisfy this, and all 4 by 4 representations. Remember, the matrices are the representations of the Dirac algebra are unitarily equivalent. I know I spelled this wrong. As you get older, you seem to become more dyslexic. I was never dyslexic when I was young, but I'm becoming. Okay, now I don't want to go into this too much, but obviously, like, different books use different representations. Peskin and Schroeder is going to use what they call the Weil chiral representation. If you read Borkin and Gell, they use what's called the energy representation. And there are others. And even within representations that are called the same, they sometimes are different. What I want to point out is that the representation is not, while they're unitarily equivalent, the representations themselves are not unitary. All finite dimensional representations of the Lorentz group are not unitary. The unitary representations are infinite dimensional. That's why we use fields. That's something you learn when you have a non-compact group like the Lorentz group, that because it's non-compact, its representations won't be unitary. So just something to keep in mind. So if we're working in four-dimensional Minkowski space, Peskin and Schroeder use the what they call the Weil chiral representation. They define their matrices, gamma 0, 1, 0, gamma I, 0, sigma I, minus sigma I, 0. These are all the zeros and the ones and the sigmas. Sigmas are the Pauli matrices. These are the block diagonal 2 times 2 matrices. So this is the most important, probably part of the chapters, the representation of the gamma matrices. And the Lorentz generators, boost and rotation. They're given by S0I is equal to minus I over 2, sigma I 0, 0 minus sigma I. You can get this just by calculating from the formula I gave before in terms of commutators. And Sij is equal to 1/2 epsilon ij k sigma k 0, 0 sigma k. So basically it's the same as the Pauli, but it's doubled for the rotation. This is also sometimes defined as 1/2 epsilon ij k sigma k. Okay. And a 4-component field psi that transforms as above is called a Dirac spinner. There are other kinds of spinners, things like, I don't even know how to pronounce the guy's names, Majorana spinners and Weil spinners and so on. So this happens to be a Dirac spinner. Now, then, we present, PS presents the famous Dirac equation. I gamma u partial with respect to u minus m psi of x equals 0. Psi of x is a 4-component object, psi 1x, psi 2x, psi 3x, psi 4x. Notice that this is a different space. This is spinner space. If it was the same, if it was in a space of space-time, we would go like psi 0, psi 1, psi 2, psi 3, but it's not. And then these Dirac spinners, they transform as psi of x, and I'm always leaving out the spinner indices most of the time. Lambda to the 1/2 psi lambda inverse x. This is sort of what psi prime at x prime is defined as. Now, theoretically, I should put like an index A here, and then I'd have a A and a B here, then I'd have a B there, So I left off the spinner indices, and now I put them in, and then this would be A. Anyway. And lambda to the 1/2, which I didn't define, lambda to the 1/2 is defined to be e to the minus I over 2 omega mu nu s mu nu. So this is sort of weird, but the omega is like omega 0, 1, omega 0, 2, omega 0, 3. These are the boost parameters. The infinitesimal boost parameters. And then like omega 1, 2, omega 2, 3, omega 3, 1. These are the rotation parameters. Usually you would see these as theta, for example. Okay. So then this following identity, which I won't derive, but it's shown in the book and sort of derived. This is quite useful. It's quite useful for showing the covariance of the Dirac equation. So I have lambda inverse. Now these lambda to 1/2 matrices, which I first introduced above, these are not the lambda matrices. Lambda is the space-time transformation matrix. Lambda is a space-time matrix. And lambda to the 1/2 is a spinor transformation matrix that corresponds to lambda. So anyway, the identity is lambda to the minus 1/2 gamma u, lambda to the 1/2 is equal to lambda mu nu gamma nu. So this is sort of like, on this side, you could think of this as like U inverse gamma u, the usual transformation of an operator. And on this side, this is just a vector transformation. So this identity is sort of saying that we can take seriously the vector index on top of the gammas. Now, PS show the covariance, and I'm going to show it. Covariance of the Dirac equation. They put in most of the steps, but they leave out one tricky step. It's not really that tricky, but I'm going to put it in just in case you got stuck there like I did for a while. First of all, we have our space-time transformations. X mu goes to X prime mu equal A lambda mu alpha X alpha. Okay, that's our Lorentz transformation. Now, we can multiply this equation by lambda inverse nu u. So what do we get? We get lambda inverse nu mu x mu is equal to lambda inverse nu mu lambda mu alpha x alpha. But these two equations are, they're just, m inverse m, basically. The u indices line up perfectly. So this is just the identity matrix. So this is the delta nu alpha x alpha, which is equal to x nu. So that's how you invert the Lorentz transformation. So now from this we can easily see that the partial of x nu with respect to, I left out a prime here, with respect to x prime mu is equal to lambda inverse nu mu. And now, using this, I can get, using the chain rule of calculus, the partial with respect to x prime mu is equal to the partial with respect to x nu times the partial of x nu with respect to x prime mu. This is just the chain rule of calculus. So this is equal to, since we established this over here, this is equal to lambda inverse nu mu, the partial with respect to x nu. Okay. So now I'm going to go back to the PS derivation. In the unprimed system, x mu, the Dirac equation, is I gamma u, the partial with respect to u. Remember, we always have this. And if we have the partial with respect to mu prime, partial with respect to x prime u. So I gamma u, the partial with respect to u, minus m psi of x equals 0. Okay. In the prime system, we want to make sure that the Dirac equation holds in the prime system. The equation becomes I gamma u. We don't transform, when we make a space-time transformation, we don't transform spinor matrices. That's the key thing to understand. Partial with respect to mu prime minus m, mass is a scalar invariant, or at least that's how we're starting with our theory. Psi prime x prime equals 0. We want to see if this implies this. That's what we have to show. Okay, so let's massage this. First of all, I can write this as I gamma mu. Now remember, I have this equation up here. And so I want to use that. So I can write this as lambda inverse nu mu partial with respect to nu minus m. And now if you remember how psi is defined to transform, we get lambda to the 1/2 psi lambda inverse x. That's how psi prime x prime transforms. Okay. So that is equal to that. This is equal to, now I'm going to multiply, pre-multiply by lambda to the 1/2 and lambda to the 1/2 inverse. Okay. Now here you have to understand that this is a spinor. spinor matrix. This is a spinor matrix. This is a space-time matrix. This whole thing over here is space-time. And this is a spinor. So you can bring this through the space-time because they act in different spaces, so they don't even see each other. They sort of commute. And then we're left with lambda spinor 1/2 to the inverse gamma u lambda to the 1/2. And we use that identity that I said before was a crucial identity. And so now we get lambda to the 1/2 times I lambda mu sigma gamma sigma lambda inverse nu mu partial with respect to nu minus m psi lambda inverse x. Okay, so on the m term, you can see that this lambda to the 1/2 and the previous lambda to the 1/2 inverse cancel. On the spinor term, the more complicated term, we use that identity which transforms this into a space-time Lorentz matrix. Now, if we write this in the proper order, notice it goes down to up to down on Lorentz matrices. So I have I lambda inverse nu mu lambda mu sigma gamma sigma. Again, space-time and spinor things can commute. We don't have to worry about it. Partial nu minus m psi lambda inverse x. Now, these two are inverse matrices. Notice the indices line up perfectly. So this becomes lambda to the 1/2 I del nu sigma gamma sigma partial nu minus m psi lambda inverse x. Now this is equal to lambda to the 1/2 I gamma nu partial nu minus m psi of lambda inverse x. And now the Dirac equation says that this is equal to 0. I know it's at a different space-time point, but the Dirac equation holds at all space-time points. So we have the Dirac equation in the prime system is also 0. Okay. And it's very easy to see that the partial mu plus m squared psi equal to 0. This is the Klein-Gordon equation. So every component of psi satisfies the Klein-Gordon equation. It's a standard definition everywhere, I think, to define psi bar equals psi dagger gamma 0. And this, using this definition, we then have psi bar psi is a Lorentz scalar. Which is what we want for building Lagrangians. The transformation of psi bar goes to psi bar lambda inverse 1/2. You might have thought that psi dagger would do it, but it's not that convenient. It just doesn't work out that way. We need that gamma 0 matrix in there. And the Dirac Lagrangian, which leads to the Dirac equation, is then L Dirac psi bar I gamma u partial u minus m psi. And you can see, you can get two equations. You can treat psi and psi dagger as different fields. Seems crazy to do that, but it's not that hard to justify. And then you'll get the Dirac equation, and you'll get the adjoint of the Dirac equation. Now, let's talk about Weil spinors, and we'll finish up Weil spinors. If you look at the generators, the S's, they're block diagonal. So this implies that the Dirac equation is reducible. Now, I said earlier that we were going to look for irreducible representations, and so why are we allowing this reducible representation? And the answer is because we added, without telling you, parity. We added a parity transformation because until the late 50s, 1950s, parity was thought to be a universal symmetry. Okay, but with the overthrow of parity, especially for the weak interactions, we need to rethink. So for strong and electromagnetic interactions, parity is still a good symmetry. And we need the Dirac equation. For weak interactions and massless particles in general, we should look at the irreducible two-dimensional representation. So we write psi as equal to, we separate out the upper and lower components. We call the top component psi left, the bottom psi right. And these are, two component psi L are two component spinors. And they transform under infinitesimal transformations rotations, theta, boost, beta. We have psi L. I'm sorry. One minus I theta dot sigma over 2 minus beta dot sigma over 2 psi L psi R goes to 1 minus I theta dot sigma over 2 plus, this is the all-important difference in sign there, psi R, and the two coupled equations become I, the partial 0 minus sigma bar minus sigma dot del psi L minus m psi R equals 0. I partial 0 minus sigma dot del psi R minus m psi L equals 0. Now if m equals 0, the equations decouple and we get the Weil equation. First, let me define sigma mu, 1 comma sigma I, sigma bar u, 1 comma minus sigma I, and the Weil equations, they become I sigma bar dot the partial of psi L equals 0. I sigma, that should be a sigma. I sigma dot the partial of psi R equals 0. These are the Weil equations for left and right-handed particles. Okay, I'm going to stop here. I'll come back on the next video, part B. We'll do the solutions of the free Dirac equation, and then we'll quantize using anti-commutators, and then we'll show some invariants, vector and tensor and scalar invariants of the spinors, and then we'll do time reversal and charge conjugation and parity transformations as well. So a lot still to go here. Thank you very much. I'll see you next time.